Alright, in this video I'm going to go through the review for Chapter 9. So, temperature is a measure of the average kinetic energy of the particles. When the temperature of a substance increases, then the volume increases due to thermal expansion. I have two beakers of water, one at 70 and 80, and they're poured into a larger beaker. What's the final temperature of the water? The final temperature should be between 70 and 80. A substance registers a temperature change from 20 degrees to 40 degrees. What temperature change does this correspond to in Kelvin? Well, I would convert 20 degrees to Kelvin, and then 40 degrees to Kelvin, and then subtract them. And you will find out that there's 20 degrees difference in Kelvin because there's just a 1-to-1 difference between Celsius and Kelvin. There's not a scale change difference. And energy is transferred as heat between two bodies in thermal contact when they differ in their temperature. And the use of insulation in the outer walls of a building is to minimize heat through by conduction. Sandpaper gets hot when it's rubbed against metal because friction causes the temperature of both things to increase. In the presence of friction, not all the work appears as mechanical energy. Some of it is converted into internal energy, causing the internal energy of the system to increase. A nail is driven into a board with an average kinetic energy of 140 joules. And if there is no potential energy change, then that means all of that is converted into internal energy. So if it's 140 joules of kinetic, that means it's going to be 140 joules of internal energy. And during a phase change, the temperature remains constant because we have that nice flat line. As the temperature increases, the motion of the particles means the particles are going to move faster. And if they move faster, that means they're going to have more kinetic energy. In 12, we have a pan of water, and it's at 80 degrees, and it's placed on a block of porcelain at 15. When those two reach the same temperature, they're going to be at thermal equilibrium, and it will be closer to 80 degrees because water has a very high specific heat. So it means when those two finally reach the same temperature, it will be closer to the water than it will of the porcelain. And if energy is transferred from a metal container to the air, that means that the temperature of the metal container has to be higher than the temperature of the air, because it always goes from a higher temperature to a lower temperature. And the specific heat of a substance is the energy required to raise 1 gram of a substance 1 degree Celsius. And I have two bottles. They're placed in tubs of water. The first one, the bottle is at 40 and the water is at 20. And in the second one, the bottle is at 55 and the water is at 35. So in this case, they're both going from the bottle to the water because in both cases, the bottle has a higher temperature than the water. So they're both going in the same direction. And between 40 and 20, that's a 20 degree difference. And between 55 and 35, that's also a 20 degree difference, which means not only is it going in the same direction from the bottle to the water, but the rate is also the same because the difference in temperatures are the same. Alright, so now we have one of those lovely phase change diagrams. And what happens to the ice at 0 degrees? Well, at 0 degrees, it's going to start to melt and turn over to water. And at 100 degrees, what's happening to the water is it's starting to evaporate. And then between 0 and 100, they're asking what's happening to the water. And that as energy is added, the temperature increases as the kinetic energy of the particles increases. Okay, the next one is a temperature conversion. So if it's 38 degrees Celsius and I have to find it in Kelvin, I would add 273. And since I have 1 after the decimal point, I would have 1 after the decimal point in Kelvin. To find Fahrenheit, I have to take it times 9/5, and then I'm going to add 32. And when I take 38 times 9/5, I'm still going to have 3 significant figures, which has 1 decimal place. Now when I add 32, I still need to have 1 decimal place, so I get 100.4 degrees Fahrenheit. Here I want to find the increase in internal energy at the bottom of a waterfall. So the internal energy is going to be the same as the change in the gravitational potential energy. So I'm going to do mgh. I plugged in my height and I plugged in g, but I don't know m, so I just used m. I multiplied those two numbers together and I get it's 1,420 times the mass. And since I don't know the mass, that's all the more I can have my answer. And that would be labeled in joules. Next one, they want to find the temperature increase of 4 kilograms of water when it's given 4,800 joules of heat. So I used my specific heat equation. I plugged in the amount of heat in joules. I plugged in the mass. I plugged in the specific heat of the water. And then I wanted to find my temperature change, and I calculated a temperature change of 0.29 degrees Celsius. And it has two significant figures because this one has 2 and this one also has 2. Okay, now on to number 22. This is one where we have to find the final temperature and we're mixing copper in with water. So the copper is going to lose energy, that's why it's a negative, and the water is going to gain energy. So I'm going to do my mCp delta T for the metal, mCp delta T for the water. So I plugged in the mass of my copper, I looked up the specific heat of copper, and on your test that would have to be something that was given. I don't know the final temperature, so I did F minus 98, which was the initial. Plugged in the mass of my water, the specific heat of my water from the chart, and then I did F minus 21. So then I took this times this, and then times F, and then I multiplied that times 98 to get this number. And then again distribute 250 times 4,186 times F, and then 250 times 4,186 times a negative 21. Then I had to get my F's together on one side, so I was going to bring this one over, and then I have to get my numbers on the other side together, which I did here, and then I'm going to divide, and I get 22 degrees Celsius. So we can see that the water didn't heat up a whole lot because I had so much of it, but the metal cooled down quite a bit. All right, and then how much energy is required to vaporize 35 grams of water? They give me my heat of fusion and my heat of vaporization. Well, since I'm just vaporizing, I just need to use the heat of vaporization. So I took the mass, which was 35, times my heat of vaporization, and I left this in grams since this label was grams. Multiplied the two, and then I rounded it to two significant figures, and I got 79,000 joules. And that's the end of the review for Chapter 9.